The end is near. All right. So the key question is, do you remember your name? Zoom does, in case you don't. So these tables, this is why actually, anticipation of this is why I've split the study sets. I actually like this. So your study set for Thursday will start out with a table like this, as will your worksheet. And so hopefully by Thursday, these tables will be just clicking and you'll be able to cruise through them. So the key is figuring out when one of them changes and the other one doesn't. So when we look at the comparing the first and the second, the NO changes, but the hydrogen does not. And it can be actually easier to compare the second one to the first one because that's when it doubles. And so when the NO doubles, this goes up by 4. And so that would mean NO 2 to what power equals 4? And that would be 2 to the second power. So NO is going to be to the second power. Rate laws are always written as rate equals K, and it is a small k. Those of you who are taking the summer term, when we get into equilibrium, it's a capital K. So in German, the word constant is spelled with a K. C doesn't exist in most languages, so K is often used as a constant. All right, to compare when the NO doesn't change here when we compare 2 to 3. And we can see the hydrogen, when we double the hydrogen, the rate just simply doubles. So when it's a straight relationship, whatever you do to 1, it does it to the rate, then you would just say it's first order. And so first order, just we can leave the 1 off, or you can show it. That's a personal preference. So these are the orders in respect to the NO and the hydrogen. All right. To calculate, so what it is every chart that you have, you're going to create a simple algebraic equation and based on the chart. And it just takes practice. And so that's what you have one here. There's one on the worksheet. We'll see one as we go through the notes tonight. To calculate the rate constant, we're going to do the rate divided by the NO squared and the hydrogen. And you can plug in any set of data from the table. That equals K. And it doesn't matter. To be boring, I usually just put the first set of data in. The other thing is to put in your units. So moles per liter second. The book that I plagiarized this chart from, that's how they always showed the units. You can also show it as molarity per second, so capital M per second. And NO 0.420, and that is just molarity or moles per liter, and that's squared. And the hydrogen's 0.122. So that's where we get this number, the 6.32. Usually the number is not a big deal. It's the units, and that is a small piece of it, but this is also good practice because a lot of you are going to be going into physics next year, and physics, you're always dealing with constants. And the constants, the units of the constant are always to make the rest of the equation work. The hard part with rate laws is the K has different units every time. So this moles per liter will cancel that one. So we're going to have molarity squared and seconds, but they're both in the denominator. So you either can say m to the minus 2, s to the minus 1, or you can do it how I did it here when I wrote the answer, where I said per m squared s. So in the rate law, the molarity is always in the denominator if there's a molarity in there. All right, calculating the rate of appearance of the nitrogen. So again, we just plug in. So the rate equals to our formula up here. We just plug in the K with its units and then the numbers. So 0.333 molarity squared and then the 0.222. And again, you can say moles per liter or capital M. Please do not say molarity per liter because that's not legitimate. And you can see this molarity squared would cancel that, and we'd have the molarity per second, and we get my number. Now, the next one is a similar idea, right? That we'd plug in our numbers that I give you, which is 0.123 molarity squared, 0.321. And when you punch that in, you're not going to get my answer. What you're going to get is a number that is moles per liter second, and that is going to be the data table, and the rate law and the K that we calculated is for the rate of appearance of the nitrogen. So this is technically going to give you a number that's moles of nitrogen per liter second. So you have to do one more step because I want to do the disappearance of the NO. And just a quick comment about vocabulary, don't get caught up in it. If it is a reactant, the reactants are disappearing because they're reacting. So you're always going to have less and less and less. The products are going to be appearing. So that's why it's called the rate of appearance of nitrogen. Yeah, sometimes I just say rate, but that's what, and then here we're looking at the NO. So we would do a mole to mole ratio that there's 1 mole of N2 for every 2 moles of NO in our balanced equation. And that's where I got my number with, should have units. So again, moles per liter second. If you want, you can say moles of NO, but that's, sorry, that extra step is the data table will always tell you what when you're talking about. All right. So for the next question is we're going to be doing the natural log of AT over AO equals negative KT. I always learned it as capital A's. So these are just your initial and this is the initial concentration. And this is always assuming first order decomposition. And as I mentioned last week, the vast majority, like probably over 90% of things are first order decomposition, probably over 98% of things. These units can be any units because it's a ratio. You can have any units as long as they're the same because the units are going to cancel. And so that makes this much easier. Today, when we do the lecture, we'll do a second order one, and we have to change the units in that case. So we just do natural log of our 2.56 milligrams and 2.50. So not much has decayed yet. We have not yet reached a half-life. And then that will equal negative K, and I have another purple pen. And this was our 4.321 minutes. So the units for time, if it's in minutes, you can keep it in minutes. Some people, you don't have to always go to seconds. Sometimes it will be hours, sometimes it will be years. Just go with whatever the problem gives you. So we'll divide by the time, and that should give you your K value. It is a decay, so that's why the negative is there. So the K is always a positive number. And looks like we have 3 sig figs. So each the -3. And since we're dividing by minutes, that's why it's per minute. So the K is always per time, no matter what it is you're dealing with, because it's always multiplied by the time. So that's our first step. And again, always stating the formula, show how you filled in and you solve. And then our second step is the natural log of 1/2 equals negative K T1/2. And again, that's the symbol for half-life. It's just a T with a 1/2 there. It's saying how long for half of it to decay. So you just plug the K in, take natural log of 1/2 divided by that negative K value, and we get 126 minutes. The key is going to be being able to explain that it makes sense. And it is that up here, when we'd done the initial 4.321 minutes, there's several ways you could explain it. Only a small amount decayed. Right, so it only went from the 2.56 to 2.50. So we're nowhere near a half-life. It doesn't matter what the percentage is that decayed. You can see it's just a small amount. We're not at a half-life yet. So the half-life must be much longer. All right, any questions from the first page? We can go through this in record time. All right, which is good. I made chili today and it's really good. And I unfortunately sampled it during office hours. So now I'm hungry. All right, the same type of problem. And this one's a little bit different because I gave you the half-life. So the 245 minutes is the half-life. So your first step is the natural log. If you're given the half-life, your first step is to do this. And you solve for K. So, right, we do natural log of 1/2. And we would divide by the 245 minutes negative. Move our negative over. That equals K, which is like 2.83 e to the negative 3 per minute. Everything does have units here, so please make sure that's probably the hardest piece. And so if you're at least today, get where you can do the calculations, and then for Thursday's study set, work on getting the units and fine tuning that. So that's our first step. And then our second step would be this formula. So it's AT over A. A0 means at 0 time. So the initial amount equals negative KT. So we would plug this K in. This would be my initial amount, the 3.3, and this would be my final amount. And so we would plug in and you should get my answer, 9:57 minutes. So you can plug it in. I didn't ask if it made sense, but in this case, of course it makes sense. If the half-life was 245 minutes, the half-life, if we started, is for half to decay. And we're at much less than half. So it went through several half-lives. And that's why it's 950. So it's more than one half-life. It's more than 2 half-lives. And so the answer makes sense. All right. And then number 7 is the temperature formula, which, again, you guys have a huge advantage because you don't have to remember any of these, right? I guess green's going to be our color tonight. So natural log of K2 over K1. And again, it's the natural log of that ratio is negative. So both these formulas, there's negative there over R, and then 1 over T2 minus 1 over T1. And we'll do one of these at the end of our notes today also. The R that you're going to use, yeah, we'll go ahead and plug in. So this is my K1. So I'll put that on the bottom, 1.618 per second. And there's my K2, so 3.14159 per second. So, all right, natural log of that, we're going to have to move the R over. So we're going to multiply by R. And this R is a new R because we're working in joules. So it's 8.314 e to the negative 3 kilojoules per mole K. So that's our new R. So I'm just rearranging by moving the R over. And then I'm going to have to divide this whole thing by the T's. So it is T2 first. So that's going to be, you have to change it to Kelvin. And then T1 would be our 247 Kelvin. And what's going to happen is you'll get a negative answer. And that is because there's that negative here. So, and it's because we're dealing with, a lot of this is dealing with decay. So K's are always positive answers. Times are always positive answers, whether it's a half-life or something. Concentrations are positive. The K's are positive. Activation energies are positive. The negatives are just in the formula. So at some point you have to move that negative over. And you should get my answer, the 4.14, which is kilojoules per mole. I always do these in kilojoules because activation energies are usually huge. You can tell by the numbers that I made up these numbers, since it's the golden ratio in pi, that this is actually a really small activation energy. They're usually in the hundreds. And yeah, when you do one on the worksheet, change in temperature, a small change in temperature, if you have a large activation energy, will make a huge change in the K value. So just keep that in mind. For our next one, we're solving for K2. So K2 is our unknown. You're still using the K1 from up here, the 1.618. You're using your activation energy. Remember, there's negative. If your answer doesn't make sense, I guarantee it's a negative you forgot, because that is like 80% of the time the mistake. So kinetics is just a bunch of number crunching. So you just have to put the time in. These are really our formulas that we'll be using, is this one, and we just put them in. And we'll do practice with each of them today. But it is different, but it's just number crunching. R, you can just say R, and again, it's this R we're using now. And then we would put in our new temperature is this, which is 242 Kelvin. And our old temperature was the 247. I always solve for K2 since it's in the numerator. So you can punch this whole thing in first, and then you can get rid of the natural log. So we'll do this again today in the notes. To get rid of the natural log, you do e to the power. So again, on your calculators, it's what's above the natural log key. So that is little e as opposed to capital E, because capital E is times 10 to the power. So e to that. So whatever you get over here is going to be e to this whole thing. It doesn't mean you're better if you can do it all in one step. So having done this for many years, usually I put the problem on the board and you guys work on it, and I go around and I can make suggestions, which is a little awkward to do in this. But I would put all of this in and then do e to the power of that. Remembering looking at this, if your answer doesn't make sense, it's almost always that you forgot that negative sign. And then once you get that in, you have to move the 1.618 over. And so you'll multiply 1.618 times that whole thing, and you should get my answer. The units will be whatever the K units were. So you may have noticed I love this question. It showed up all last week in our solutions homework set, and it's showing up all this week. So our temperature, we went to a colder, we decreased the temperature, right? It got colder. And the temperature is all about kinetic energy. It means you lowered the kinetic energy, or how I like to talk about it is you have fewer giggles and jiggles, which is really kind of sad. So everything's moving slower. Everything has slowed down. Lower temperature, it's why we have refrigerators, because it slows everything down. It slows down the decay of our food. So the lower temperature means it's slowed down. And if we look at our rate law, our K went lower. So slower means lower K. K is always proportional to the rate. So if K goes down, that means the rate went down, and that makes sense. If the temperature went up, then everything's moving much more and it's going to go faster. So K would have gone up. All right. Questions?